Hi, this is Professor Gutierrez, and today we will be looking at Chapter 4, Probability. In particular, this one will be Chapter 4.1, Section Basic Concepts of Probability. Figure it's probably better to start with the basics and going into like the advanced stuff right away, because that's just kind of confusing and it has all kinds of Greek letters, but you've already learned some Greek letters, so we don't want more. We're going to get more. Sorry. But no Russian letters, so we're not going to get any yas, so happy about that. It's a backwards R, by the way. Addition rules, complements of conditions, probabilities, and Bayes' theorem, like Beowulf without Grendel. Counting. Yes, you're going to learn to count. That sounds really condescending, but it's really weird. There are different ways you have to count, especially if they're big numbers. And section 4.5, we are not going to do probabilities through simulations, available at triololostats.com, whatever, I don't care. All right, what are probabilities? Well, probabilities are numbers. I will give you a number. It will be somewhere between 0 and 1. It can't be greater than 1. It can't be less than 0. All right, a small probability, such as 0.001, corresponds to an event that it rarely occurs. Now, rarely occurs may mean rarely occurs for a single item, and it may be something that you see often, simply because there are a lot of different things. Give an example. If it's in the fall, you see leaves falling all the time. The probability of an individual leaf falling at any particular second is rather small. But there's so many leaves that chances are you will see a leaf falling. That's why it's called fall, rather than autumn. It's called autumn too, so that didn't work too well. All right, next are odds and how they relate to probabilities. Odds are commonly used in situations such as lotteries and gambling. Not really a lotteries and gambling kind of person myself, but yeah, to each their own. Some people like them. They got flashy lights. They pump oxygen into the rooms. If I have to go there with friends, I generally do the penny slots. Basics of probability. What do we got? We got an event. Now, an event is a collection of results or outcomes of a procedure. Great, that doesn't really explain much. It's simply an outcome. So I can have a kid or I can not have a kid. So those are two different possible outcomes. I could also say, how many kids do you have? Well, I have an odd number of kids, or I have an even number of kids. Those are also events, but they're not simple events because they are collections of results. Odd number of kids could mean 1, it could mean 3, it could mean 5, etc. A simple event is an outcome or an event that cannot be broken down further. So if I say odd number, I can break that down further. If I say 1, I can't break that down further. And whether or not you can break it down further really depends upon what the event is you're describing. Because sometimes the event can be what is the number that the die has when it rolls. So that could be one thing. You could also ask when the die rolls, where is it? How long does it take to roll? All that. So your sample space could include all that data too. But if you need to know what your sample space is. Sample space, by the way, is the next one. And it procedure consists of all possible simple events. Now this could be finite, like a die. It could be 1 to 6 or 1 to 20 if you got a 1d20. 1 to 100 if you got a 1d100. I got one of those. A single 1/100. I've seen 1/1000s before. Those are cool. I don't have one of those. No. And this is going to be the collection of all possible simple events. So we got A, we got B, and we got C. Possible events. Great. All right. Now this is going to give some examples of simple events. Now, when an event is called a simple event, that does not mean the event itself was simple, that it was easy. For example, in this, they say the procedure to give birth, because giving birth is simple. Oh yeah. So single birth, example of an event. 1 girl, simple event. The sample space is all possible simple event. That could be 1 boy or 1 girl. 3 births, 2 boys and 1 girl. Now that might seem like a simple event, but it's not, because for this one they are considering that order is important. Now order isn't always important, but in this case it is. Now that's not something they actually mention here, but it does happen to be important here. And we know that simply by the sample space that's given. So 2 boys and a girl could mean you had a boy, you had a boy, you had a girl, you had a boy, you had a girl, you had a boy, you had a girl, you had a boy, you had a boy. Any of those. All possible sample events: boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. Amazed I got all those right, I think. Now you can check me, see if I got them right. All right, simple events. With one birth, the result of one girl is a simple event, and the result of one boy is another simple event. They are individual simple events, cannot be broken down further. At least hopefully not. That would be weird. 3 births, you have the 2 girls followed by 1 boy. That could be broken down further, as we saw. Now, oh wait, no, this one, sorry, they're saying is 3 births, the result is 2 girls followed by a boy, so that's girl, girl, boy. That is the simple event. All right. When rolling a die, in this one, whenever they say die, this is singular for dice, and they always consider a 6-sided die. The outcome of 5 is a simple event. The outcome of an even number is not, because an even number could be 2, 4, or 6. Solution: not a simple event. With 3 births, the event of 2 girls and a boy is not a simple event, because it can be, it can occur in 3 different ways. There's so many different beautiful, beautiful ways to have 3 little kids. But notice that here we're only concerned with sex and order. Those are the only 2. We're not concerned with how much time between them. Are they triplets? Or anything like that. And notice that the girls here are interchangeable. No comment on society there. But the fact that girl, girl, boy is only a single event, and it doesn't matter which of the girls is first. Simple events and sample spaces. All right. We got 3 births. We got sample space of 1, 2, 3, 4, 5, 6, 7, 8. Wait, no, 8. Yeah. So we got 8. With 3 births, sample space consists of 8 different simple events listed in the above table. We got 2 possibilities for the first, 2 possibilities for the second, and 2 possibilities for the third. 2 times 2 times 2 is 8. And we got 8. Coinkydink? I think not. It's not. We're going to learn later. It's not. No. Notations for probabilities, because we got to write stuff down. We're not going to be like, oh, the probability of X is this. Probability, it's a long word. It's complicated to spell. So we use a P. The P right here. That denotes the probability. A, B, and C could be certain events. A, boy. C, girl. C, intersex. All right, that is indeed a third possibility for sex. Let's see. Probability denotes the probability of event A occurring. So notice in this case, if we're talking about male, female, intersex, we'd be talking about 3 different sexes. But, well, intersex, whether it's an event anyway. I'm not sure if you'd call it a different sex, but it's certainly a sex event. The probability of A and B are about equal. The probability of having a girl is actually a little bit higher than the probability of having a boy. Probability of C is very low. Intersex births are about 1 in 2,000. Some cases people will have surgery afterwards. Some cases they won't. Is this right? Is this wrong? Don't know. Not really the class to talk about that. But the 1 in 2,000, that is a good number to have here. All right. So, and if you don't know what intersex is, a really simple way to do that, you can Google it, look it up. If you want pictures, well, Google's not going to give you those kind of pictures unless you look up like intersex animals or something like that. And you're welcome to do that if you want. Again, not part of this class. Explore on your own if you want. If you don't worry about it. All right. So the probability of A, P of A, denoted the probability of an event A occurring. And I usually say P of A. P of B, P of C. P of C, remember I said, is 1 in 2,000. I give a fraction for that. So P of C is 1 in 2,000. 1, something is certain to happen, most likely. Here, something is likely to happen. 50-50 chance means equally likely to happen. Now, be very careful with 50-50. People overuse and abuse 50-50 so much. And 50-50, notice, is also 1-to-1. So it's going to be the same thing there. But a lot of people will say it could be A, it could be B. 50-50 chance. You could be right, you could be wrong. 50-50 chance. You could live, you could die. 50-50 chance. No, 50-50 chance doesn't just mean there are two options, so, it's 50-50. 50-50 chance means you have some knowledge. Right? You have some knowledge, and you are saying that the probabilities of the two being correct are equally likely. That's what you're saying. You're saying you know that is true. Now, let's say you are on a test and you're guessing between two answers. True-false test. So you're guessing. And you have no clue what the idea is. The chance of you guessing and getting the correct answer would be a 50-50 chance. Now, in that case, I just told you have to have knowledge, and you don't have knowledge. So how can that be a 50-50 chance? Well, the fact is you do have knowledge. You know the answer is either true or false. You definitely know it has to be one of those. So in that case, your chances of being right are 50-50. Unless you happen to know, let's say you know this teacher likes giving true answers. Then your chances would probably be higher if you picked true. All right. Unlikely. Probably not going to happen. 4%. Now, unlikely does not mean it will not happen. There was about a 4% chance prediction that Trump was going to be elected president the day before the election. And that did happen. That was an unlikely event, but it was not impossible. It did occur. It did. All right. So how can we find probabilities? There are a couple of different ways to do it. Now, one of the most common ones, and I think one of the ones you're probably most familiar with, is people just pulling it out of their backside. This is recording, so I'm going to say backside. They will just, the probability of that's 10-to-1. Well, first off, that's not a probability, but that would give you about a 90% chance or something like that, or a 0.9 probability. And that's just someone making something up. Or the odds of that are impossible. Impossible aren't odds. Don't do that. So be careful of people making up statistics. They do it 90% of the time. And I just made that statistic up myself. All right. So how can we figure out probabilities? Relative approximate frequencies of probabilities. Related frequency Relative frequency approximations of probabilities. So, conduct a number of independent experiments and see how many times the event occurs. The probability of A occurring, divided by the total number of times the procedure was repeated, is going to tend towards the probability as you do it more and more often. So this is a good way to do it. If you have time, you have the ability to experiment. This is not necessarily something you don't want to do if you can't repeat. Right? So like nuclear war is probably not a good idea to do this with. Have a bunch of nuclear wars, test out what stuff happens. Not going to work well. A couple of reasons. Number one, nukes kill a lot of people, so we don't want to do that. And number two, they would not be independent, because once you've had one nuclear war, then you start having more, and then there's less people, and then Poland invades Russia, and Cuba annexes Spain, the world turns upside down. It's horrible. So don't do that. But rolling a die, right? You do it 200 times, like you're going to do in that little procedure I gave you. And then you will divide over the number, take the number of times that a certain outcome occurs, divide it by the total number of times you did it, 200, and you will get the probability of it, relative probability of it. You'll also compare that with a estimate in your in the example I give. All right, now if, and this is a big if the probability of all of the outcomes are equally likely, you can simply say the number of ways that A can occur divided by the total number of possible outcomes, S divided by N. This one is a good one, and people abuse this one horribly. What are the chances that this is perfectly shaped to that? It could be any shape, and it's this shape. You know, this proves X, Y, and Z. No, it don't prove anything. All right? Requires equally likely outcomes. If you have something that governs the outcomes that does not make them equally likely, then that is not going to work out. Like, you know, isn't it amazing that all the planets are spherical? I mean, we got 9 planets, including planet X, which we haven't found yet. And all of them are spherical. But they could be so many different shapes, you know. The odds of each one of them being a sphere is, you know, 1 out of 1,000, because they could be 1,000 shapes. You know, that's just amazing that they're all spheres. No, it's not. There's a reason that they're all spherical. It's called gravity. There's a guy called Desert File. He gets upset when people ask about that. He has this weird gravity thing he talks about. Oh, equally likely outcomes. Got to make sure. We're not going to have any cubic planets. Or cube planets. Didn't the Superman enemy... Never mind. That was a cube planet. Alright. And subjective probabilities. Estimates by knowing knowledge of the relative circumstances. Probability of it being a sphere, if it's big enough, pretty much 1. And this is estimated using the knowledge that we have, gravity. Exactly what I just did there. Simulations called Monte Carlo simulation. It may seem kind of strange because Monte Carlo is also where people do gambling. And where people who gamble want to do simulations to estimate possible probabilities. Oh, that might be related to it. But yeah, if you know the physics behind it, or if you know the governing principles behind whatever's going on, then you can make a rough estimate of what simple interactions could happen and figure out what possible outcomes could be with different, what are called seeds. And these can be used to get probabilities. Are we going to do these? No. Well, not in this class anyway. Rounding probabilities, 3 significant digits, so like 0.111, 0.572, 0.896, stuff like that, or 0.0324. Right. Now we do want to round them if they are 0.5 or higher. So look at this, 2/3 is 0.66666, going on forever. Happy, bye-bye. Now we want to get it 3 digits, so that's going to be 0.667. Right, and 5/9 is 0.5555, going on forever. We're happy with that. So that's going to go around to 0.556. That's how we round them. Law of large numbers. All right, repeat something again and again. The relative frequency of the events tends to approach the actual probability. And I talked about that when we were talking about that. Not an incorrect statement, but not particularly useful. Hopefully you know what I mean. Because I forget exactly where I talked about that. All right, caution, use of large numbers. They only apply to large numbers. If you do something just once, it's not going to apply to a single event. You know, odds are 2 to 1 that I'll win. What are the odds? Well, 2 to 1, and you just lost. So that's not fun. All right. If we know nothing about the likelihood of different possibilities, we should not assume that they are equally likely. The actual probability depends on factors such as the amount of preparation and the difficulty of the test. Test? Yeah. All right. Oh, this is a lovely one, isn't it? Find the probability of dying while making a skydiving jump. Well, let's see. In a recent year, there were about 3 billion skydiving jumps. 3 billion? 3 million skydiving jumps. And 21 of them resulted in deaths. We use the relative frequency approach as follows. Skydiving deaths. Number of skydiving deaths divided by the number of skydiving jumps. 21 over 3 million, 0.000, bunch of 007. I wonder if those 21 people were killed by James Bond. Maybe. Maybe. Classic approach. You know? We just take a bunch of people doing it, and we do the data. Let's take a look. In a study of U.S. high school drivers, it was found that 3785 texted while driving during the previous 30 days. 4720 lied about texting while driving during the same period, and they claim they didn't, so we say they didn't. Right. Based on these results, if a high school driver is randomly selected, find the probability he or she texted while driving during the previous 3 days. All right, so we're going to say these people didn't, these people did. Add them together. That's the total pool that we have. So we have 3785 over the total, and that'll give us the probability. Add them together. Boom, boom, boom. Total number right there. And we can now review the relative probabilities. Probability is the number who texted while driving over the total number, which is 0.445. Right? If we want to do that as a percentage, and some people like doing it percentages, 44.5% of them texted while driving. But the probability of a single one texting while driving when you ask, or the result, the probability of you getting that result is 0.445. Okay, just what I said. Boom. Complementary evidence. Events. Are these events that say nice things to you? No, they're not events that say nice things to you. They should be. They're like them out saying, hey, you did a good job. Wow, it's so awesome. I love you. No, they don't. Compliment just means everything that you're not. That kind of sounds insulting to think about it, but that's what it means. So we got A, and then we got A with a little line over there. That's called A bar. And that consists of all outcomes in outcomes in which event A does not occur. In a recent year, 3 million skydiving, 21 of them resulted in death. Find the probability of not dying while making a skydiving jump. Well, that is 3 million minus 21 divided by 3 million. So 2,999,979 jumps survived. Take that, divide by 3 million. Boom, we get a bunch of 9s followed by a 3. So that's the probability of not skydiving while making a death. Wait. No. The probability of not dying while making a skydiving jump. I certainly don't want to die while making a skydiving jump. I don't. Now, does this mean skydiving is safer than, say, driving? I don't think so. And this is the reason I say this. There are a lot more people who die in a car. That's for sure. But a lot more people use cars, and cars are used a lot more often. So if you did it per trip, then I suspect your numbers would be about on par, if not lower than this. And I suspect if you did it per mile for like airplanes, you would get an even lower number. Very safe. All right, rare event rule for inferential statistics. Inferential, that sounds like demonic or something like that. All right, you have a certain assumption. You get a certain probability for it. So I assume this. Therefore, this should be my outcome. Lo and behold, I don't get that. However, if you consistently get something that is less than, significantly less than, or significantly greater than what you typically would expect with that assumption, you can conclude that the assumption is probably not correct. You assume, oh, it's going to happen this way, and it never happens that way. Then something might be wrong with your assumption, if your assumption leads to that conclusion. Right? It's testing a hypothesis. We like doing that. We like testing things. Right? So how do you know if something is significantly high or significantly low? Well, you look at it and it needs to be less than about 0.05, depending on what you're checking out. But we'll use 0.05 for now. So significantly higher or significantly lower. Because this just went from high to low. That's it. Nothing big. All right, review. Probability of an event is a fraction or decimal between 0 and 1. Probability of an impossible event is 0. Probability of an event that is certain to occur is 1. Probability of A is equal to probability of A. Probability of A bar is equal to the probability that A does not occur. All right, odds. We don't talk about evens. No, odds. They're special. All right, so this is for gambling. The actual odds against an event A occurring are the ratio, the probability of the complement of A divided by the probability of A. And is usually expressed in the form A colon B. So that's a ratio of A over B. Yeah, whatever. A to B. Or not to B. No, that's a question. Where A and B are integers. Yeah, that's if possible. Not always possible. But you try to round it so that they're integers if you can. All right. Reduce if you can. If A is 16 and B is 4. Express the odds as 4 to 1 instead of 16 to 4. All right. Odds in favor of an event occurring are PA, the probability of A, divided by the probability of not A, or A bar. So A to B, B to A. That makes sense. Payoff odds, because if you're a gambler, you get paid off a certain amount of money. Otherwise, it wouldn't be called gambling, it'd be called mugging. That sort of is mugging, but they have fancy lights, and they sometimes give you free drinks, so it's kind of nice for some people. Payoff odds against an event A occurring are the ratio of the net profit if you win to the amount of the bet. So the payoff odds of event A are net profit to amount bet. So if I bet $5 and I get 180 back, then my net profit would be 175. So that would be 175 to 5. Notice that it's not what I get back. It's not what I win. It's the net profit. Okay? We do have to watch out for that. So you bet $5 on the number 13 in roulette. Probability of winning is 1 in 38, but the payoff odds are given by the casino as 35 to 1. Seems as if things are in the favor of the casino here. Find the actual odds against a 13 occurring. All right, we'll do that. Find how much net profit it would make if you win 5 on 13. Well, 5 times 35 is 175. And if the casino is not operating for profit and payoff, the odds were changed to match the actual odds against 13. How much would you win if the outcome were 13? You would win nothing because the casino would go out of business. But that's probably not the answer they're given. Now, the probability of a 13 is 1 over 38. The probability of not a 13 is 37 over 38 because it could be anything else. Odds against 13 are probability of not 13 or probability of 13. 37 over 38 divided by 1 over 38. Fraction over a fraction. How do we get rid of that? We can flip the bottom fraction, or we can just multiply top and bottom by 38. We can do that. We're smart. We have calculators. We just cover up the right side here and then say 37 over 1. So 37 to 1. All right. The casino payoff odds are 35 to 1. We have a 35 profit to the net bet. So 35 profit for each dollar bet. A $5 bet is worth 175, which is 5 times 35. The winning bettor, I don't know. Would collect 175 plus the original 5 back after winning. The total amount collected would be $180 for a net profit of 175 for the bettor. Sounds exciting and alluring. But that's why the casinos make money. If the casinos did not operate for profit, payoff odds would be changed to 37 to 1, the actual odds. Again, it's the 13. Payoff odds of 37 to 1. There is a net profit of 37 for each dollar bet. A bet of $5 will give you 185. Casino makes a profit by providing a profit of only 175 instead of 185. That would be paid with a roulette game that is fair instead of favoring the casino, which is not a roulette game. Now, that does not mean everything a casino does makes a profit. I'm going to say everything a store doesn't make a profit. Sometimes they have things to pull you in, like Costco's $1.50 hot dog and soda. They can't make money off of that, can they? I mean, it's like an awesome hot dog. And then a soda that tastes good? No. Make profit off of that? Maybe. Maybe. But I don't think so. And that is it for section 1. Just over 30 minutes.